Hi. What we're going to look at in this podcast are some of the reactions of thiols. Just a brief discussion of their unique character, but also remembering that there are strong parallels with oxygen chemistry. So we're going to start off, first of all, again with a type of chemistry that you should be very familiar with, and that is the alcohol analogous reactions. And one of the things we know about alcohols is that we can take an alcohol and react with a carboxylic acid. I'm showing the general structures here with the R and R1 being various substituents. You can find appropriate examples of this if you do some subsidiary reading. So the general reaction shows that if we react alcohols with acids, we get an ester plus water. This normally takes place in the presence of an acid catalyst, just to accelerate the reaction, because the kinetics are not terribly favourable in these reactions. We've got an exactly analogous reaction that occurs with thiols. Thiols can make thioesters. We're going to find that this is a particular thioester, and you'll see why I make that comment in a moment. It's a very analogous reaction. Both chemistries take place better in the presence of dehydration conditions, and in modern chemistries often this type of coupling reaction between an acid and alcohol or a thiol takes place with a dehydrating coupling reagent. Now, an example of this is something called DCC, which is dicyclohexyl carbodiamide. You can look that up on Wikipedia. And the essence of this coupling agent is that it takes water away from the reaction and encourages the equilibrium to the right hand side, thereby completing the chemistry, because normally these reactions are 50-50 true equilibrium. This product with the thiol is known as a thioester, and you'll see why that is singled out as a term in a moment. Because if we modify the chemistry and we can create these species, this is a thioacetyl chloride. And that is analogous to an acid chloride that you probably have seen before. You've seen the podcast, this particular podcast. Thioacyl or thioacetyl, thioacyl chlorides can react with alcohols to give thioesters, and in this case, if it's a chloride, the other product would be HCl. Now, this thioester is actually a thione ester, and both the thiol ester and the thione ester are known as thioesters because they contain sulphur. But this tells them apart. The terminology I've mentioned tells them apart. Okay, we'll leave the esters behind and move on to thioethers. Ethers are the type of functional group that most students will come across in passing. Obviously, thioethers would be a little more rare to discuss those pre-undergraduate courses. So let's have a look at this chemistry, and it's directly analogous to the sort of chemistry that can take place with alcohols. We've got a primary halide, in this case it's a bromide on the left hand side of the equation, and we're going to react it with a thiol. We can establish an equilibrium, and we can create thioethers, and in this case a secondary product, HBr. Now note, these reactions are pH dependent, and we can sort of have a feeling for that when we realise that thiols dissociate to their thiolate ions plus H+, depending on the media. If the media is particularly polar and it can support solvation of ions, we can get a significant proportion of thiolate ion. And the thiolate ion is the better nucleophile. If you think about it, the thiolate ion will have three lone pairs of electrons surrounding it, whereas a thiol will have only 2. So the reaction often takes place with a base present, and you can have a separate base as a reagent that's going to deprotonate the thiol, or you can take the reaction can take place in the presence of a basic non-nucleophilic, or at least poorly nucleophilic solvent. It has to be poorly nucleophilic or non-nucleophilic because we don't want the solvent reacting with the alkyl halide. So what happens in this case? Well, we have our alkyl bromide, our primary bromide in our reaction. We generate presence of thiolate ions. Now, if we have a base present, often the base has to have a lone pair of electrons, and the base is often neutral, and if it picks up the proton off the thiol, it becomes charged, and then you can see that we've got a counter ion there. The thiolate ion attacks the electrophilic carbon and releases bromine as Br-, and we get a substitution reaction. And here's our Br-, and that would counter ion with our base plus hydrogen.